I've been meaning to document this for a while. In electrical engineering courses, they always tell you about the full adder, the half adder, the ripple carry adder, basically ways of adding binary numbers. But they never actually show you what's inside the chip. I mean, you can crack a chip open, but it won't tell you much. You'll just see a piece of metal with some lines in it. It's impossible to figure out what's in it. So I reproduced a large-scale 4-bit relay adder. In short, you enter the numbers here, and that's a 0 and that's a 1, from least to most significant. So that's 1 in the first register that you see. That's another 1 in the second register that you see. That's the adder itself, and that's 2, because binary counts different than decimal. So I'll now give a basic introduction of binary, and then I'll explain how this model works. On this board, I've spelled out the basics of the binary system with a comparison to decimal. In the binary system, the lowest digit here is a 9, 109, 109, in decimal, regular numbers. You can put in each place in decimal, you can put a 0 through a 9. And so 109 in decimal. That's 9 ones, 0 tens, and 1 times 100, equivalent. We can convert this to binary, but the binary system only has 2 possible values for each place, a 0 or a 1, whereas decimal, well, you have 0 through 9. So binary is inherently different than decimal because whereas we have ones, tens, hundreds, and everyone in middle school is taught this, in binary, and binary is 2-state, you can only have a 0 or a 1 in each place, and so it goes up 1, 2, 4, 8, which are powers of 2 starting at 0 and moving forward. So, to convert 109 in decimal into binary, what we do is we list off the powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, and then you take the number 109 and you find the one that is still smaller than 109, but the closest to it, which is 64, and then that would give you 64. You can take 32 and add that to it, which is 96. That's pretty close to 109. And then, so you take the difference between 96 and 109 and find out it's 13, and you can add the 13 back by adding 8 to 4, which is 12, and then 1. And so, 109 in decimal, which is only 3 digits, is a bit longer in binary. It's 0, 1, 1, 0, 1, 1, 0, 1. But my key point here is decimal increases in powers of 10. So you have ones, tens, and hundreds in each adjacent number. And binary is powers of 2. On the next board, I'll do some basic calculations in binary. Continuing from the last segment, we're going to cover simple addition in binary. And it's noted because binary only has 2 possible values for each bit, it's much simpler than decimal. The decimal problems over here, we all had to memorize these tables in elementary school. But in binary, I can explain the tables very simply. In a simple case of 2 bits added together, there are only 4 cases. 0 plus 0 is nothing. Nothing plus nothing is nothing. 0 plus 1 or 1 plus 0 is simply 1 alone. And when we add 2 ones, 1 plus 1, well, that would give us 2 if this were decimal. But it gives us a 0 in that position, and you carry over the 1. For 2 single bits, this is the only possible states for the addition. Now, you may wonder, well, if you have a series of bits, like if we had 2 bits added to another 2 bits in binary, what would happen if you carried over 1, is in the instance we had 1, 1 here. That leads to 3 bits being added, and again, there's only 8 possible cases, 2 to the 3, and they're listed here. All zeros is 0, any 1 in each of the 3 is 1, any 2 follows this one here and gives us 0 with a carry of 1, as in this case, and that case. But in the instance where you have 3 bits being added, and a bit is a binary digit, a 1 or a 0, if you have 1 plus 1 plus 1, that would give you 1, 1. In other words, it would give you 1, and then you carry over 1 to the next column. So 1 plus 1 plus 1 in decimal is 3, and in binary it's still 3, and this place is 1 and this place is 2. In decimal, you can add them together to prove it. Now you may wonder why all the explanation here. Well, the machine I've shown in this video does basic addition in the binary regime, but let's start with decimal. So 3 plus 4 in decimal is 7. Everyone knows this. Now, if we take the 3 and we convert it to binary, you get 0, 0, 1, 1, or 2 plus 1, which is 3. If we take the 4 and convert it to binary, you get 0, 1, 0, 0, which is 4 alone. When we add them together, we use the table presented here, which is universal for this math. 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, and then nothing plus nothing is nothing, which gives us 0, 1, 1, 1, or 4 plus 2 plus 1, which is 7. And so we verified that addition works between these two. Okay, so I've continued from the board onto my engineer's pad here. So let's consider the problem 3 plus 4, which is 7, and base 10, which was shown by the subscript here. This is called the radix to indicate that it's decimal. Now in binary, if we remember from the last example, we have 1, 2, 4's place, and 8's place. And so 2 plus 1 is 3, so that's the same. And 4 alone, 0, 0, 0, and it's the 4, is the 4, so that's 3 plus 4. And what we can do is use the table I gave on the last slide. 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0. And this gives us this answer, and we can put the radix of 2, which in this case is binary, B-I-N. You don't have to include the radixes as long as you know which one is which. That was a simple example with no carries. A half adder could in theory do this, but the full adder is the one that's actually used. So we have 6 and 12. So 6 is obviously, remembering the convention, 4 plus 2. And 12, well, it is 8 plus 4. And when you shift everything over by a place in binary, it's the same as multiplying by 2. So 6 is this and 12 is that. But that fact is used in shift-add multipliers and things of that nature. So this is 6, and this is 12, and we add the same way based on the table. 0 plus 0 is 0. 1 plus 0 is 1. 1 plus 1, remember, is 0 in this column. Carry the 1, which is here. But then we're faced with a dilemma. 0 plus 1 would be 1, but we have another 1, so 1 plus 1 is 0, and we carry 1. So it's overran the 4-bit position. These are the first 4 bits, and we have a bit here. So as we know, we have 1s, 2s, 4s, and 8s, and this one is 16. So if we have 16, and we add the 2 that's represented over here, then what we get is 18, which is what is desired. As you can see, right and equivalent. The final problem we have is 7 plus 8, and we've seen 7 before, 0, 1, 1, 1, or 4 plus 2 plus 1, which is 6 plus 1, or 7. And 8, remember it's 1, 2, 4, and 8. So when we add these, it's 1 plus 0 for those 3, and then 1. So this gives us 1, 1, 1, 1. Now this is actually 15. And when we have 4 bits, as in this particular example, you can run from 0 through 15. 4 bits is a nibble, N-Y-B-B-L-E. It's not used because it can only store 16 possible states. If we had 8 bits, so if we had one more next to this, as in the example when I converted 109, it would run in the positive domain from 0 until 255. And that is a byte. So a byte equals 8 bits. Alright, so I've shown these problems and explained how they were equivalent between the binary regime and
the decimal regime. So decimals up top, binaries on the bottom, and these are the same. And now I can show how the machine I made and introduced solved these same problems. And the machine automates the action of multiple full adders in a cascade, which represents the tables I showed earlier, the 8 possible combinations. And one full adder does each place. And the inputs and outputs are essentially switches and LEDs. So let's move over to the machine and keep our results here in mind. Okay, this machine here, I called it the Numerac. It's essentially a binary adding machine. So although I will detail its architecture, it's not very complicated, on paper at least. You have one register here, another register here, and they get added together by this mechanism here, and the result is displayed here. So from the previous one, I showed this problem here, 0011, 0100. Let's enter it in. So essentially how this thing works, if the switch is in the up position, it's a 0. If the switch is in the down position, it's a 1. So 1, 1, in other words 1, 1, 0, 0, and we throw this switch here, and when we do so, it's represented in this register here. As you can see, there's LEDs behind it, which is the second register. Alright, we can look at the output, and it shows 0, 0, 0, 0, 1, 1, or 3, which is the same value as on that register. The way the machine is aligned is you have your least significant, or your 1 position here, and your most significant, or your 8, over this way. So it's the same way with decimal. We have from ones to hundreds. And so now what I can do is I can take and enter 4 or just a 1 in that position, 0, 1, 0, 0, and we can toggle that in. And as you can see, I'll show you it there. And so now we have both 3 and 4, and the result 0, 0, 1, 1, 1. This one here is the overflow. I'll show that in a second. But we have 7. 3 plus 4 is 7. Wow, it takes that much electronics to figure that out. But it can be done. And you could, in theory, cascade these things forever to have more and more space. In fact, early computers were, in the 40s, little more than this board here multiplied on a grand scale, and they filled a room and used kilowatts of electricity. All right, we have 3 problems. 1 is done. Let's go to our next one, 6 plus 12. So what we can do is enter 6, which is 1, 1, 0, 0. We can toggle this one, and you'll see it entered in the bottom one, 0, 1, 1, 0, 0, 0, 1, 1, 0, per the convention. And then now we have to add 12, and so we can go ahead, 1, 1, 0, 0, that's 12, and this one is the back register. So toggling this one is the front register being set, toggling that one is the back register, so we toggle that one. All right, that's 12, 1, 1, 0, 0, 0, 1, 1, 0, 6, 12 and 6. What do we get? We get, on the LEDs, 1, 0, 0, 1, 0, all right? And if we look over here, 1, 0, 0, 1, 0, 18, or we have the 16 plus a 2. Again, it's the binary convention, of course, 1, 2, 4, 8, 16 is the next one. This is an overflow. That's why there's not a 5th switch right here. Okay, so we did the first 2 problems correctly. Now we have one last problem here, which is 7 plus 8. We know that it's 15, but let's see if our machine knows it's 15. So we enter the 7, which would be that, and we toggle it in the right register here. All right, 0, 1, 1, 1, that's 7. And then what we can do is enter the 8, enter that in the next register. All right, 7 plus 8, and we get 0, 1, 1, 1, 1, and 0, 1, 1, 1, 1, 15. So it did all 3 problems correct. And I think the tactileness of this, machine is something of some slight beauty, but it works, and you can perform addition this way. You might wonder what's the highest addition it can do, and it turns out the highest addition it can do is 15 plus 15. I think I showed this earlier. Let's do it again. So we have 15, which is the 4 ones. We toggle that into the front one and the back one, and as you can see, it gives us 11110. And as I mentioned before, that is 16 plus 8 plus 4 plus 2, which it turns out is 30. Anyhow, I hope this video is interesting. I can give the circuits of the adder itself. These are merely register or latching circuits, which are set and reset by these switches here. So we can set them to 0, and that gives us back the 15 stored in the back register, and that clears the machine completely. So as you can see, every time it cycles, you can see it. Anyhow, it's interesting to note that the first computers were very little more than this apparatus here, multiplied by, say, about 10. Later on, the electromechanical relays that you can hear clicking were replaced with vacuum tubes, thyrotrons, transistors, and other things. I hope this video was interesting, and if you want to know how the circuitry works, it's fairly simple, and I'll have another video on the relay full adder. And for those who don't want to build this, which is understandable, I'll show you the chip you can buy for $1, which does the same exact function, and maybe you can have some fun building your own binary calculator. Anyways, I hope this was interesting, and please see the future work.